Welcome, ladies and gentlemen, to our technical forum here on the group exhibit Hydrogen and Fuel Cells. Please sit down, have a drink on the house. We have coffee, tea, and soft drinks for you. The ladies are waiting for you and to serve you, and we are waiting for you to discuss with us, because our next topic will be quite interesting as well. That's about Microlith fuel reformer and fuel processor systems, and we are waiting from Precision Combustion, the Director Marketing and Business Development, Mr. Anthony Anderson. Here he is.
Hey,
welcome, Mr. Anderson.
Thank you.
Thank you to have you here. Here's your presentation.
Good afternoon, and thank you for joining me this afternoon. I apologize for my voice being a little gravelly. I've been by myself and talking for the whole week, but it's been good conversations. I'm going to talk a little bit about Precision Combustion, the company, some basic slides on our Microlith catalyst technology, and then talk about some applications and show you some pictures and talk through some prototype components and systems that we've developed. There we go. So Precision Combustion is a small, privately owned company, been in business since 1986. We're in North Haven, Connecticut, USA, between Boston and New York. We have two core technologies, Microlith catalytic reactors and then RCL catalytic combustors. For a variety of applications, fuel reforming and processing, oxidation, working on power and energy applications, and also doing some integrated systems as appropriate. We collaborate with the U.S. government. We're a U.S. government prime contractor and subcontractor, and we collaborate with large and small corporations and national laboratories and others, and focus on developing these technologies into products and manufacturing limited volume prototypes. To give you an idea of the product technology application space in the power area, you see we have fuel reformers and processors for fuel cells. This could be for APUs, for gensets, vehicles and ships, a lot of mobile applications. Working on IC engine, modified IC engines, tactical gensets. UXV, just using that generically for unmanned everything, aircraft, underwater vehicles, ground vehicles. Basically the fuel reformers and processors for fuel cells that go in those systems, as also reformers for industrial applications. Some combustion markets and applications as well, various burners and oxidizers and combustors. We do work with air cleaning, mainly for NASA applications, but also for buildings and aircraft. And then some specialty hydrogen generation for gas to liquids opportunities, and some catalytic igniters and chemical manufacturing opportunities. And then you see a variety of prototypes that we've developed in operation. The Microlith reactor technology, which is the platform we base our fuel reformers and fuel processors and the catalytic oxidizers on, think of it as a mesh type substrate, or like a window stream. And you can see right over here where we have the wire of the mesh with an interfacial layer, and then the wash-coated catalyst on top of it. And we have a semi-automated coating line, and we make it in rolls. And so the Microlith technology, unlike microchannel technologies, which are heavy and have high pressure drop, these are ultra compact and operate in a short contact time manner. They have rapid thermal response, so they're like a thermocouple, and they come to the gas temperature very quickly. So you have high heat and mass transfer, and you have high surface area per unit volume, and which helps enable low cost, because you're using platinum group metals catalysts, which can be expensive, but you're using them in a very appropriate way. And so when you compare a conventional monolith, so think of the catalytic converter on your car, or you might even use it for reforming or oxidation, as compared to a mesh type catalyst, your geometric surface area, meters squared per liter, is over 2.5 times greater in a Microlith reactor. And so you have very small channel lengths. Your length to diameter ratio is 0.3 as compared to 70 to 120 for a honeycomb. And you have the same open area in the front, but what the difference is when you have the high velocity gas going through a monolith, you form boundary layers. And so you have platinum, or platinum group metal or reforming catalysts that aren't doing any work, where within the Microlith substrate, the layers of the mesh, very little to no boundary layer is formed. And then you also have some mixing regions which help balance the reaction as well, and helps you to do a good job with either reforming or oxidation processes. And again, another comparison to show the compactness of the technology. If you compare propylene oxidation in a long channel monolith, ceramic monolith or metal monolith, 7 microlith elements, which would be about 40 thousandths of an inch or 0.11 centimeters thick, would have the same level of conversion. And so you basically have equivalent conversion with a 20-fold size reduction. So much, much smaller in size, which also translates into much lower weight. So it enables itself for mobile applications. It's more efficient use of the catalyst surface area. And again, I mentioned the mesh type catalyst. It acts like a thermocouple, so you have very rapid thermal response. And so as your temperature changes, your microlith catalyst in blue can come to temperature within a second, whereas monolith catalyst takes several seconds to come up to temperature as well. So it has a very fast transient response catalytic substrate structure. And so some of the benefits of that is when you look at full oxidation reactions, which give off a lot of heat, and partial oxidation reactions, which give off hydrogen and CO and some heat, you want to make sure you're selective to these partial oxidation reactions so you operate at a cooler temperature than otherwise you would. And then also another benefit of the technology is you see, if you look at an experimental reactor where you're looking at positions 1, 2, 3, 4 millimeters through a mesh bed, you can see that almost all the methane, in this case methane, is almost reactive by the time you get 2 millimeters into the bed. This helps you with some durability aspects as well, because if you ever have some kind of poisoning issue or you have a catalyst is damaged, the first layer might stop working, but then the next layer just keeps working and it just works its way through the bed. And you can see some of this experimental data here in operation. So as you would expect, you get about twice as much hydrogen as CO when you look at the mole percents. And so this lends itself to having the 2-to-1 ratio that, for example, gas to liquids folks might look at for a synthesis of liquid fuels coming from gas. Precision combustion uses this microlith mesh technology for 3 different fuel reforming processes. So there's catalytic partial oxidation, which we define as being with fuel and air only. And you see a couple examples of a small CPOX reactor for diesel, and then a 5 megawatt thermal for natural gas. It operates at pressure, as you can see from the thick flanges. We also have catalytic autothermal reforming. This would be with fuel, with steam, and with air, which we've done with diesel and natural gas, various fuels. There's a couple examples of a 5 kilowatt thermal, and then a person standing next to a 1 megawatt thermal fuel processor using autothermal reforming. The third technology is catalytic steam reforming. We define that as being, it's catalytic on the exothermic side, where the burner is a catalytic oxidizer, and then on the inside of the tube is a reforming catalyst. Both of these catalysts are meshed, and we've done this with diesel and with natural gas fuels. And we have ongoing programs developing this technology toward products and applications. You can also use this technology for purification, and as far as water gas shift reaction to reduce carbon monoxide within the reformate stream, we have preferential oxidation of CO, carbon monoxide, which also reduces the carbon monoxide in the stream. We've done integrations with partner companies that have membrane separation technology, and so palladium membrane or other membranes, and we actually operated our steam reformer into a membrane to make hydrogen from low sulfur diesel. And then also we have some adsorbent technology we've developed, but we work with commercial pressure swing absorptions when you go to scale up to larger sizes where that technology makes sense. Commercial applications that we look at are basically all mobile applications for the most part, aircraft APUs and truck APUs and et cetera. Also some industrial syngas opportunities producing hydrogen, carbon monoxide, HICO mixtures. For those customers that care about that, we do a lot of our fundamental development work, however, under U.S. government Department of Defense contracts, which actually has many of the same applications, or mobile applications for either aircraft, ships, or trucks, et cetera. And so we leverage off of that, and then we want to go toward these commercial applications as well. So the PCI innovation is a sulfur-tolerant logistics fuel reformer and fuel processor. It's ultra-compact, and it's able to convert diesel and these other military fuels into and other liquid fuels, for that matter, alcohols and biofuels, et cetera, to a sulfur-free syngas. And it's uniquely compact and sulfur-tolerant. The value added is, we trademark, we put the fuel in fuel cells. So fuel cells generally can't run off any fuel by itself. You have to do something to change the fuel slightly to make it operate in a fuel cell best. And so we have the fuel reformers and processors for solid oxide fuel cells, for diesel and military fuels. If you had a water gas shift reactor, you can also go to HT.PEM type fuel cells. And then with hydrogen separation, you can go to high quality hydrogen for hydrogen generation, or even if you low temperature PEM if you so desire. So I talked about earlier about the ultra compact nature of the reactor itself, but when you look at it from a system level, these fuel processors and reformers are up to 3 times lower weight than competitive offerings, 6 times smaller in size than competitive offerings. So they have faster response and lower pressure drop as well, and all this translates in the smaller size and weight, as you can imagine, intuitively can be significantly reduced cost. And so our PCI designs, we do our own system modeling with Aspen and working on our own, and with our partners, we're able to model the fuel processor and those components listed, the injector, the steam generator, the sulfur removal system, and also the balance of plant, pumps and blowers, the heat exchangers, etc. And then working with a stack, and for this example, would be a solid oxide stack, and then managing those control flows of the reformate the flow, making sure it's thermally balanced, and having the control handshakes go back and forth between the fuel processor and the solid oxide fuel cell. Some examples of some components we've developed. Here's a 1 kilowatt electrical size fuel processor to be targeted for a solid oxide fuel cell. It's 5.5 inches tall and 3.5 wide, so comparing it to a soda can here in this picture. Includes the catalyst, the steam generator, an igniter to start it, a startup glow plug, and then a sulfur cleanup module in the bottom here. And you size this sulfur cleanup module based on the maintenance cycle of your mission or your application that you so desire. It's basically a zinc oxide type sulfur removal. All the sulfur compounds are converted to H2S during the reforming process, and then we absorb it in the zinc oxide at the bottom and remove it, such that the reformate coming out is much less than 1 part per million hydrogen sulfide. We also have water recovery technology. We can operate this under water neutral conditions and recover the water and put it back in. And in a recent development, this particular model, we're able to go up to the full 3,000 parts per million sulfur content that is in military fuels today, so we can use the gamut of JP8 and JP5, et cetera, and of course sulfur road diesel that you can buy today. Another fuel reformer, a little bit larger, 40 kilowatts thermal. It's about 17 kilograms, for the reformer, the mixer, injector, and then the sulfur removal bed. We've developed the balance and the control strategy around this and have delivered this to a customer that's a solid oxide fuel cell company. They've actually integrated this technology, and it's being delivered to a government customer for a test here later this spring. And so the key to this is that also this device, even though it puts off about 10 kilowatts electrical of power, it's only going to need under 100 watts for the balance of plant components, the fuel pump and the air blower for this system. Another one here, a fuel processor for HT.PEM or LT.PEM. This is 25 kilowatts thermal, so let's say maybe 5 electrical. And so we can add a water gas shift onto this system, and we've made a couple of these prototypes that have been tested with collaborators at the University of Maryland and Ballard Power. And again, this has the fuel air and steam injector, the igniter, the sulfur removal bed, and of course the water gas shift reactor that you see in the bottom. Then you have to put it with a membrane separator or other device for LT.PEM, or the reformate should be at 1 to 1.5% carbon monoxide, so you could go into an LT.PEM that's a robust system. Give you an idea of some of the compositions in the first row. We see the equilibrium calculations for JP8, a steam to carbon of 0.9 and an atomic oxygen to carbon of 0.95. You can see representative calculations of what it should be, and we can get very close to equilibrium with experimental data. And also important is the higher hydrocarbons, keeping those under 50 parts per million. Those are coke precursors. You don't want to have coke form in your fuel cell stack. And also, as I mentioned, the sulfur compounds, which are H2S essentially, are much, much less than 1 part per million. And if you add a water gas shift after that, of course, you can get your carbon monoxide down to 1 depending upon your steam to carbon ratio, and of course boost the hydrogen a little bit as well. For scale up, another example, this is a 1 megawatt thermal ATR system for low sulfur diesel, low sulfur JP8. So let's say it's 250, maybe 300 kilowatts electrical if you put this with a stack. And again, it's about 3.5 feet by 6 feet deep by 7 feet high. it has all those components that I mentioned before that you see listed. And so this is targeted for ship applications, actually. So the United States Navy is interested in having modular power on their next generation ships called Navy After Next. It's in the next decade, actually, when they're going to look to install those. But basically, you would have 2 of these fuel processors, 2 large fuel cell stacks, and then 2 inverter converter tying into the grid. They want to have a microgrid on the ship, just like you would have a microgrid in your neighborhood, for example. Another example of something, this is actually being field tested as well. This is a 1 megawatt thermal liquid fuel reformer, liquid fuel autothermal reformer, and it's actually installed at a Ford Motor Company plant in Canada, and it's targeted to reform paint solvents from their paint process, and then later on further processed for a fuel cell stack in that process. So they save money by not having to take the paint solvents that are waste and burn them at a regenerative thermal oxidation facility, and they get a little bit of electricity back for their plant area, and then of course they have a nice green marketing story to talk about as well. Another example of scale up, this is actually 5 megawatts thermal. This is natural gas, catalytic partial oxidation. This was done for a customer interested in industrial syngas at pressure. And so this actually has gone through some performance tests. We've had 1,000 hours of durability operation. The target is 8,000 hours, and it looked fairly stable and flat for that 1,000-hour test. And in fact, we just had interest from the customer that they've tested it independently now and are interested in purchasing more units, so we're excited about that. Example of our steam reformer, again for the diesel or natural gas. It's a catalytic burner going into the steam reformer, and so you have lower peak temperatures by operating it like that. We can operate it at higher pressures. You can see the flanges are a little thicker on there, so you can use it with a membrane type separation device, and you can achieve thermodynamic efficiencies at low steam to carbon ratios. And again, something of interest is that it uses a catalytic oxidizer rather than a flame burner. And in a traditional steam reformer, you might use a flame burner, which means you're making NOx and you're making carbon monoxide emissions potentially. So that's all I have for now. I'll be happy to answer your questions, or if you would like to come back to my booth, I'm right over here, about 3 booths over in D76-1. I'm Tony Anderson, Director of Marketing and Business Development, and there's my email address as well. You can call my direct extension in America, and we can talk about what we can do to bring some of these technologies and prototype products towards your application and your needs. So thank you.
Thank you very much, Mr. Anderson, for this informative and interesting presentation. So, is yet any question in your mind, or do you want to make any comments or remarks right now? So, not yet? So,
not yet.
Thank you very much for the invitation, for all this in the audience to your booth. You are here at the group exhibit until tomorrow, I think.
Yes.
Yeah, okay. Thank you very much.
Thank you.
Thank you. After a short break, we continue our program with the presentation from Next Energy, dealing with the topic, the role of compression on the degradation of high temperature PEM MEAs. Thank you for staying.